sum of variances. So this is for a fixed point x, right? An entire bias variance discussion has been given a test query x, the behavior of a random function. So Fix is like the random variable. So the summation overall i's of Fix plus covariances. Covariance between so you'll have to look at summation I, summation j not equal to I, covariance of Fix with Mjx. Now, how do you take it forward? What is the relation between correlation coefficient and covariance? Covariance by So how can I recover covariance from rho? Rho times sigma square. So this will be rho times sigma square. Is that correct? How many times? N? Sorry? Right. This is, it's not n square, right? It is n into n minus 1. Oh, by the way, we are looking at the average. So I forgot to say this. We are looking at this. Yeah, I forgot to mention that in the slide. This is divided by. Okay. So you'll have 1 upon n square outside, right? Whole thing 1 upon n square. 1 upon n square. And this is going to be nothing but n times sigma square. So when you expand sigma square by n plus sigma square rho 1 minus 1 upon n, you get this. This is fine. So this should get you the expression I had on the board. Sigma square by n plus sigma square rho into 1 minus n. Bloom in. And then further simplification, we will yield the expression on the slide. Okay, let's do that. One more step of simplification. Okay. So the whole goal is to try and reduce the rho and increase the n. I'll also go over the convergence, the intuition behind convergence, not necessarily all these steps. Convergence of AdaBoost. So as I said, the goal in AdaBoost is to iteratively reweigh examples so that subsequent classifiers give more importance to examples which are misclassified by the important classifiers. So you need to estimate the importance of a classifier, and that will influence the importance of examples, which will in turn influence the importance of subsequent classifiers. Because the xi was the importance of an example, alpha t was the importance of a classifier. of the teeth classifier. And alpha t, the idea is that it should increase as the error made by the teeth model decreases. So, there is a specific form, and xi I should account for the goodness of all the models so far as well as the goodness of the current model. So, xi I is xi I into something, the previous xi I, which means how has this example's weight been evolving over time, times how good or effective the current model itself is. Even if it has misclassified, the current model is not very reliable, I will not be giving too much importance to its misclassification of the ith example. So, then the question this was the AdaBoost algorithm, and the lab is about implementing AdaBoost with perceptron. So, one question we were left with is, well, why would it work? Why will this specific form work? So, I given a hint that there is actually an upper bound loss to the sum of misclassification losses over individual examples of a weighted combination of the individual classifiers that AdaBoost is trying to minimize. So, they were we kind of split the argument into 3 parts, and we will only do the first 2 parts. The first part is this upper bound that we have, which is in terms of a combination of the classifiers, a combination using scalars alpha t. This upper bound is minimized when the scalar alpha t turns out to have this specific form 1/2 ln 1 minus error due to the teeth model divided by error due to the teeth model. So, that is specifically in this tutorial 10. Okay, so, the first thing we argue is based on the convex property of the exp function. So, this is the exp function. Okay, so it is cup shaped, right? It is increasing, monotonically increasing, but it is cup shaped. So, we argue that the sum of these deltas, which is anyway upper bounded by exp of the sum of the deltas, sum of the exp of the deltas. Now, this sum of the exp of the deltas itself can be shown to have this upper bound because of the convex property. So, this is the argument here, where we are now making use of the fact that the alpha i's, the combinations, convex the combinations here. So, this alpha t's are the weights. So, pictorially this is what we are talking about. The 0,1 loss is basically situated here or here, and this curve, blue curve, is basically going to be an upper bound at all points. And you can now then use simple first principles, setting gradient to 0, etc. You can show that this upper bound is minimized. So, minimizing the upper bound is a function of the alpha takes place under this particular form of alpha. These 2 steps should be very straightforward. We are not going into the claim 3 right now, that requires a little bit more background in optimization. So, the first and the second claim is what we are concerned with. So, the tutorial problem 2 is about applying the same boosting paradigm, but for clustering. In figure 2 there are 4 clusters, I mean there are 4 coordinates, so to speak. So, a person can be a linguist or a computer scientist, but a linguist could be a student, a linguist could be the instructor or a prof, likewise with computer scientist. Now, I want to do effective clustering. What I am going to give in addition to just these points is some things, some constraints, must link and cannot link. Okay, so, let's say my perspective of clustering is based on linguist versus computer scientist as against clustering the profs together and the students together. Okay. So the way I do this is by putting some constraint. This one constraint says a student and these two, the student and prof are both linguists, so I just put a constraint between only these 2 points. And I put a cannot link constraint, saying that these 2 points cannot be in the same cluster, and the underlying semantics is that this is a linguist, this is a computer scientist. I am not really encouraging this divide between linguists and computer scientists. All I am saying is this is one way you can incorporate some background constraints. For all you know, this cross could have been a green edge and this could have been a cross, the green edge could have been a cross. So all we are saying is I want the clustering to follow some prior knowledge I have. I don't want it to be just left in the wild. Okay, and it turns out that it's a very interesting problem. This two-mean k-mean clustering problem with these constraints could be solved using the boosting paradigm. Okay, and I've also already released the solution here. So our formulation is that x1 to xn is is a collection of examples to be clustered. N is the total number of examples. Each example xi is a vector of d dimensions. So S plus is the constraint of must-link pairs, and S minus is the constraint of cannot link pairs. Now it may not be complete. I only know few. In that particular figure I gave only one must-link and one cannot link constraint. So how do you accommodate such constraints in clustering? And the hint is you can use a boosting paradigm. Okay, so what would you do? And then the next part of the problem is you can actually do it more formally using AdaBoost, like exponential form again. And here's the idea. So let's say you have the k-mean clustering algorithm. What you do here is identifies a subspace that keeps data points in the unsatisfied must-link pairs close to each other. So cluster so that the must-link can come close to each other and the cannot link are far away from each other. So you are basically weighing each point in k-means based on its importance and boost the membership of must-link points to the same clusters. So must-link is boosted, and especially you boost them when they land up in different clusters, right? So you remember when the error is high, error is going to be computed in terms of importance of examples. So if an important example is misclassified, at that iteration you give less weightage to the clustering that is performed, but then you further boost up the importance of that example which got misclassified. So it boosts the membership of must-link points to the same clusters when they land up belonging to different clusters at the end of any specific iteration. So it's basically a slight modification of the k-means objective, right? So k-means objective says sum of pairs, sum of distances of all points from every cluster, right? Now what we are doing is we are considering exponentiated form of the same. Again, the AdaBoost idea of a convex upper bound, and to that we are adding this boosting part based on the must-link and cannot link constraints.